Building a reliable AI agent often feels like watching a stripped gear. You spin up a language model, assign a complex task, and watch it grind through iterations, catching for a moment, then slipping backward into a loop of mistakes it cannot fix. This is the field's default failure mode. A survey of 70 open-source agent projects revealed that 60% of them rely on the exact same architecture, the agent loop. This diagram shows the core mechanism. The agent loop is an iterative cycle where a single language model decides its next action by reading a context window that grows larger and noisier with every turn. That structure creates two immediate problems. First, dependencies between tasks exist only inside the model's transient memory, providing no guardrails against out-of-order execution. Second, when a step fails, the system enters an unbounded recovery state, allowing the LLM to burn through tokens, retrying the same flawed logic indefinitely. Furthermore, the model can silently revise its own plan mid-execution. Once the run is over, the original strategy is overwritten, destroying any reliable audit trail for developers to follow. When an execution environment lacks explicit dependencies, limits on retry attempts, and versioned history, it cannot be engineered. It operates without structural guardrails. A 2026 position paper titled From Agent Loops to Structured Graphs proposes a solution to the structural instability. The authors treat the agent loop as a poorly specified software scheduler that relies on an opaque, non-deterministic policy. Look at the contrast here. On the left, the implicit loop. On the right, the proposed alternative, graph harness. This architecture extracts the control flow from the LLM's prompt and compiles it into an explicit directed acyclic graph, or DAG. The core design commitment of this graph is strict immutability. Once a plan version is generated and validated, its topological structure remains fixed for the duration of the run. Lifting the control structure out of the model's imagination and mapping it onto a visible graph replaces chaotic flexibility with mathematical predictability. To understand exactly how a graph achieves that predictability, we have to look at the formal mathematical tuple used to describe any execution system. This formula tracks states, policies, outcomes, and transitions. But the critical variable here is U, the ready set. The ready set defines the exact number of nodes whose prerequisites are satisfied, making them eligible to execute at any given instant. Because an agent loop generates one sequential response at a time, its ready set cardinality is locked at 1. It is mathematically defined as a single ready unit scheduler. Adding a planner or using parallel tool calls fails to break this bottleneck. The model still controls what gets parallelized on a turn-by-turn basis, meaning the concurrency is non-deterministic and unreliable. In a graph executor, the topology of the DAG computes the ready set independent of the LLM. If 4 tasks have their dependencies met, the system structurally guarantees that all 4 open up simultaneously. Parallelism depends on the structural scheduling framework. The limits of sequential inference cannot be bypassed by simply using a more capable model. Let's trace how that bottleneck plays out in a concrete task, investigating a Python authentication bug, testing a patch, and updating the documentation. Here is the task modeled as a 10-node graph. Notice the structural layout: 2 independent search queries at the top, 2 alternative patch options in the middle, and a documentation update that can run parallel to the entire testing track. If we assign this to a standard agent loop, the system ignores those parallel paths. It searches the authentication files, waits. It searches the utilities, waits. It processes all 10 steps in a single rigid line. When the model writes fix A and the tests fail, the LLM makes an ad hoc decision to pivot to fix B. It operates with no strict bounds on how many times it might bounce between failed tests and new code. The final cost for the loop is 11 distinct turns, 0 concurrent operations, and an execution history that was silently rewritten along the way. When a system lacks a topological map, it compensates by guessing its way through dependencies, costing significant time and compute. Now let's process the same task through graph harness. Here, a planner validates the entire static graph before any execution begins. The scheduler immediately identifies that neither search query depends on the other. The ready set jumps to 2, and both files are retrieved in parallel. Further down, the topology opens up again. The system dispatches fix A, fix B, and the documentation update all at exactly the same time. This concurrent execution relies on strict join semantics. A node might require an all-of join, waiting for every predecessor, or an any-of join, which takes the first successful outcome from multiple paths. In our scenario, the agent attempts both patches. Fix A fails, but fix B succeeds. Because they are connected by an any-of join, the system recognizes the condition is satisfied. It skips the recovery protocol for fix A entirely and moves straight to testing. Compressing 11 sequential turns into 6 scheduled rounds physically reduces wall clock time by turning failure management into a structural property. Graph Harness addresses the unbounded recovery problem by completely partitioning execution from diagnosis. It enforces a strict context partition. The environment where nodes execute is isolated from the environment where failures are analyzed, preventing the agent from using failure history as an implicit input. Errors are caught by the escalation invariant, a mechanically enforced 3-level ladder. Level 1 is a local retry, strictly reserved for transient errors, like a network timeout. If the error involves a contract violation, like an output format mismatch, it moves to Level 2, a local patch. The specific node is reconfigured, but the graph structure remains intact. Level 3 is the request replan. This is the absolute last resort for missing dependencies, requiring the system to halt and generate an entirely new versioned plan. Because every individual node is assigned a timeout limit and a finite retry budget, Theorem 6.2 of the paper mathematically guarantees that the system will eventually terminate. Graph Harness stops infinite loops by using an API that rejects out-of-order recovery. Safety is a function of the protocol. Graph Harness provides rigorous control, but that control requires deliberate sacrifices. This architecture is not a universal solution for every possible agent workflow. The system intentionally rejects speculative execution, often called a first-of join, where an agent races multiple approaches and cancels the losers mid-run. Stopping nodes mid-execution creates ambiguity over which commits actually count, corrupting the execution trace. The framework draws a hard expressiveness boundary, excluding competitive parallelism, dynamic topology changes, and recursive subgraph expansion. These exclusions follow a single design principle: controllability first. When faced with a choice between giving the model unstructured freedom or ensuring the execution trace is verifiable, the architecture defaults to verifiability. Graph Harness is built for engineering workflows, where a predictable outcome is more valuable than an open-ended, creative one. At this stage, the research is a theoretical design proposal, containing mathematical proofs but no empirical performance measurements. To address this, the authors constructed a rigorous 7-group experimental protocol. This blueprint is designed to isolate the performance value of every individual structural upgrade. By measuring adjacent configurations, like a raw loop versus a loop with a planner, or a planner versus a full graph, researchers can calculate attributable gains. This identifies whether an increase in success rate came from the graph topology or simply from a better prompt. Setting up falsifiable hypotheses, such as predicting that graph overhead might actually hurt performance on very simple tasks, ensures the community tests these claims scientifically. Graduation from impressive novelties to reliable enterprise software requires us to stop treating language models like magic boxes. We must stop writing loops and start engineering schedulers.